Good morning, all. My name is Guy Tall. I currently work for Limelight Networks. At the time that I wrote this presentation, I was actually at another carrier, Global Crossing, and so the idea at the time was to put something together that sort of shared some of the experiences that I had while helping to run the backbone and the MPLS implementation there. Since I had left, I actually had to strip out some of the specific information about certain incidents, but I think it actually made the presentation better to have it be a little bit more generic anyway. So I'll try to supplement with some examples if possible, but I apologize, it's not exactly the same presentation as I first put together. Okay, let's try that. All right. So what we're going to talk about is a quick overview of what MPLS is, why you'd want to use tunnels, maybe why you'd want to use MPLS specifically, discuss RSVP a little bit and some of the quirks. I'll go into a couple of examples of some issues that we ran into or that anyone that would implement it would run into. I'll go into where to place the head ends of the tunnels and some different ramifications of where you place them, whether you're going to do online or offline calculation for your reservation statements, and then I'll summarize it up at the end. So MPLS, it stands for Multiple Protocol Label Switching. Basically, packets are switched through the network along a predetermined path through the cunning use of labels. So basically, the routers have a information-based database on the router that contains a list of all of the LSPs that transit through it, which basically amounts to, label coming in on a certain interface, rewrite the label with another one, pass it out as another specific interface. It was argued it could speed up routing and whatever. There's been some debate about that, whether it actually happens or not. But it does take routing away from all of your core devices. Well, so when the tunnel establishes, it determines whatever the best path is at the time. And so, then you have like a counter on the head end that will periodically go out and recalculate, recheck to see if it's still the best path. So, real quick, these next two slides, I have diagrams from Convergence Digest from a presentation or an online course that a fellow named Rick Gallagher put together. Just throwing that out there since I actually didn't get permission from him to use the slide, or the graphic rather. I asked him, I didn't hear back, so there's the credit for him, don't sue me. So what you have is a label edge router. That's the head end of your tunnel. Determines the next hop for the prefix, inserts the label into the header, shoves it along its path. The routers in the middle are called LSRs, and they do what I just mentioned before. They see a label coming in on a specific interface. It knows with that label, I rewrite the label, repackage it with another one, shoot it out another interface. All right, let's look into the MPLS packet header in excruciating detail. No, I'm just kidding. I wouldn't do that to you guys. All right, so here's why we'd want to use tunnels. It's very useful on an operational level for seeing how much traffic you have flowing between two destinations on your network. For example, here, how much do you have flowing between your network, between a city pair. It's very easy to calculate that. I also found it useful, if we had a certain surge in traffic on our network, to be able to quickly pinpoint the two, the entry, the egress and ingress on your network. This became really useful as I moved into an engineering department. The ability to route specific prefixes along a predestined or specific tunnel, either one that gets created for a specific purpose or for like a transitory issue that's going on, or maybe just to do some traffic engineering in general, not specific to an event. And it also allows you to specify specific routers that you do want your traffic to flow through. You can either do that through a series of strict hops, which basically you can use a loopback address or an interface IP and say, all right, this is one of my constraints on my path. I want all the traffic along this specific tunnel to transit this particular interface or this particular router. You can do that with a strict, saying, it must follow this path, or you can say loose, which says, all right, so instead of routing to the end point, your destination, route to this loose hop. I don't care how you get there, but it must transit through here. So that became useful for one of our overlay networks that used a SRLG database to make sure that we didn't have, there was a primary and a backup tunnel for the specific type of traffic. And we wanted to make sure that if there was a layer 1 failure along the primary path, that the backup tunnel wouldn't share any of the same network elements, so that the tunnel was already going to be established, and it would reduce the amount of time that forwarding could restart. So it was also useful, for sort of a capacity planning function. It was kind of kitted around. We call it a poor man's net flow. A specific incident that it became really useful was there was a particular peer there was a common circuit failure between a city pair that we had, and we actually didn't realize how much traffic was being passed back and forth in the one side of the tunnel, or the one side of the circuit. So we had a circuit fail and traffic rerouted to another peering point, and it was enough where I contacted that other peer and said, hey, we should probably set something up on the A side of this circuit, because when that circuit failed, we saw so much traffic reroute to the other, to an alternate point. So it actually helped out a lot to optimize traffic flow between the two networks. It also allows you to do protocol transport through your backbone, perhaps on protocols that you don't actually intend to enable on your entire core. So it allows you to run VoIP tunnels if you decide to run it through a tunnel. You can do VPN, IPv6 using 6PE. So you don't actually have to enable IPv6, but you can still have it as a product offering. Some of the drawbacks are that it definitely adds a level of complication on your network. There's more protocols, more moving parts. It also adds a lot of overhead, and so you need to have beefier routers. So it simplifies the routing a little bit through the core, but it adds state to be able to keep all of the the tunnel information database up. You need more RAM to be able to hold all that information, and you also need to have training for your operations and engineering staffs to be able to support it. And you also have a possibility of a disconnect between your data and control plane, meaning that as your data travels along a certain path, if you go to a specific router that's not on a head end of the tunnel, and you run a trace route, you may not be following the same path because that's not going to be constrained by whatever your constraints are that you specify in your head end. But there's been some items that I'll mention in a sec that help out with that. There's also the issue of TTL propagation. One of the, when we first enabled MPLS at Global Crossing, people would just see, side A, Los Angeles, side B, New York, and hey, what's going on in between? So, one of the nice parts about it is that as a carrier, you can troubleshoot your own network without getting bombarded with emails. Hey, your path switched from here to there. So you can hide your network events a little bit better. The MPLS ping is what I just mentioned a second ago, as far as being able to run a trace route or a ping from the head end and actually have it take the tunnel. There were some tunnel forwarding issues that we ran into that wouldn't become apparent if you actually just ran a straight ICMP trace route or ping. This may not be too relevant, but it certainly was previously, where you might have some TCP benefit of having fewer hops. Some applications would time out after a certain number of hops. So a couple of customers said that they actually liked the fact that there were fewer hops in the trace route in the path. And then, of course, there's the marketing advantage of saying, hey, we're a 1-hop, 2-hop network or whatever. So some of the benefits of using MPLS, and so there's a lot of variables about, again, where do you place it and how it's implemented. But, a couple of years ago, it wasn't uncommon to have, OC48 backbone, OC48 uplinks to a router, and generally speaking, customer and peer router ports were, OC12, GigE, different variations, but usually on a scale, one order smaller than your actual backbone or uplinks. There were the larger customers and peers that would have larger interfaces, but now it's not very uncommon to have, a customer or peer on one router that has more capacity, in and out, on the interconnect than you actually have on your backbone. And then, the size of the ingress or egress circuit is actually, even if it's aggregated, you could have 2 by 10 GigE, 3 by 10 GigE, but the actual, at the core of it, it's still a 10 gig circuit. You can't have a 12 gig flow on it, for example. So having the ability to break flows down into smaller, a series of smaller flows is one of the nice elements. Allows you to defer your upgrade costs a little bit. If your network's running a little hot in a certain area and you have some additional capacity in another, you can use a different combination, either using a loose hop or using a stateful signaling protocol like RSVP to move traffic to non-direct paths. Of course, there's some considerations to take into account, which I'll mention a little bit later relating to this. And you can do different QoSs with different labels that MPLS offers. Some drawbacks are that you could have an asymmetrical data plane. A lot of times, it will follow the same path as your IGP, so it's usually not too much of a concern, but usually just something to be aware of more than an actual drawback. And as tunnels break, you will lose data in that tunnel when it breaks. Some of the benefits of running RSVP-TE lets you control your traffic levels, and what I mean by that is, there are networks that are expanding into new regions, and when they do so, they don't necessarily need to have the same scale of a network in their expansion. It allows you to open up a small POP in a new location. If your network grows, your customer base grows, then you can do your incremental upgrades. Something that became useful at different times is being able to add uneven parallel circuits where you have maybe OC48 uplinks or 10 gig uplinks, and you don't have the chassis space at the time, or you have to add another card, but you actually have available interfaces that on both sides that where you can bring up some more capacity in a pinch. And so if you were just to have strict IP, it would try to load balance equally, but having something where a protocol where you have the ability to say, I don't want you to send more than X amount of traffic along this path, allows you to use uneven parallel circuits. And you can do some link coloring to allow you to only send certain types of traffic along a particular path. One example would be if you have a node in Asia, and let's say you have better traffic like VPN traffic that wants to go to Europe, instead of having to traverse through North America to get to Europe, you can go directly on through the terrestrial part of Asia. Well, those circuits are really expensive. You definitely don't want to put your low margin IP traffic on there. So you can say, I only want my VPN traffic to be able to take this preferred path. Possibilities are endless with that. You could do some prioritization of traffic, as mentioned earlier, and it also allows you to do some more advanced error detection. It actually does polling of the network as sort of a heartbeat. It doesn't just wait for like the equivalent of a path tear message to shoot out to have to make adjustments to the path. Some of the drawbacks, you have more state. And one of the biggest part, though, is that you become reliant on having the control there. So if for whatever reason a tunnel fails, and you have some constraints that you've taken into account, when the tunnel fails, that constraint's no longer there, and you have the resultant, just direct path that IP would choose, which may not be the same path that your tunnel has taken. So if you are counting on that constraint for a specific region of your network and it's not there, it causes issues. Some of the quirks, at the time, I'd never played on hardware other than Cisco or Juniper, so this is the Cisco and Juniper implementations of RSVP. Of course, they don't implement it the same way. What Cisco's by default will do is after they don't shoot every time a tunnel establishes. It doesn't necessarily matter to the rest of the network. That a tunnel established along a specific path. But once you get to a certain threshold, you do want the router to say, hey, I'm starting to fill up. So what the Cisco's will do is every 15%, it'll flood out saying, I just crossed the 15, I just crossed the 30% barrier. One of the nice things that they do is once it starts getting full, at 95, 96, it starts every 1%, it starts flooding out saying, hey, I'm starting to reach my max, I'm getting closer to my max, and it tells the rest of the network, don't try to signal through me. What the Junipers will do is, it's just 10%, and it goes all the way to 100. So as you can guess, once you get past 90%, unless you actually hit 100, and it's pretty hard to do, tunnels will still attempt to establish through that router. So that became interesting at a certain point when Cisco devices got replaced by Juniper devices as core routers. So now, what happens when your traffic flows start to get bigger? You can allow your tunnels to just keep growing and have 4, 5, 10, 12 gig flows on a specific tunnel. You can convince your budget owner that you need to forklift your entire network, or you can split your demands into parallel tunnels. So usually most people will take option C there, but it's not a magic bullet. So this is a possible scenario that you can run into. I don't think it'd be too uncommon. You have on your left, let's say that's your point A, and then on the right is point Z, and you have your 4 parallel GigE circuits, let's say. Now the middle router there can be your network, it can be a single router, it doesn't really matter too much. What we're looking at is the uplink capacity of the 2 endpoints there. If you have 2 tunnels, let's say you had a 1 gig flow between the 2. Well, on a single GigE circuit, that would fill the entire circuit up. So that's when you're like, all right, I got to split it up into 2 tunnels. And it would just establish through, 2 of the tunnels. And let's just say, for sake of argument, that you actually have like a even distribution across your 4 uplinks. If one of the tunnel fails, the other tunnel will take all of the actual traffic, but it's only reserved half a gig. It's carrying 1 gig of traffic. So now your circuit utilization, instead of having a nice 4 by 60% distribution, you have 2 circuits that are 60%, one that had the previous traffic on it running at 10%, and then the 4th circuit is now at 110%. So something to stress, I guess I should have mentioned earlier, is that there is a disconnect as far as the reservation. The tunnels are not necessarily aware of how much traffic is actually passing through it when it reserves. So it'll take whatever number you have for your reservation. So they're actually, one thing to keep in mind, though, basically the takeaway from this is that, so there's your actual traffic along the tunnel and your reserve traffic for the tunnel. If you use, well, I'll go into the online and offline calculation in a little bit here, but it can definitely cause a big issue when you have parallel tunnels. One of them fails, the next tunnel, the remaining tunnels will soak up all of the difference. If you were just running IP, it would probably, spread across all 4 tunnels. So your head-end placement, the 2 different philosophies were to put all the tunnels on the core routers or to put it on the edge. Some of the benefits of putting it on the core would be that generally a lot of people run 2 core router environments, and you can have multiple edge, not just for IP, but a lot of people use different hardware to aggregate VPNs and whatever. So you can have fewer tunnels on your core. It also allows you to have kind of a dumb edge where you just have cheap hardware that can take the traffic in or push the traffic out and doesn't really need to have too many moving parts. So the benefits of actually pushing it to the edge, though, is that you get better accounting across your network. It allows you to run the RSVP or MPLS on your uplinks, so you get the traffic management all the way to your ingress or egress point. And there's no slosh. I was talking about that with someone yesterday, where slosh is, the traffic will, or the router, the edge router will see two tunnels on two separate routers as being a valid next hop. So there were times where traffic would flip-flop between both uplinks and from tunnel to tunnel. So when you have edge to edge, if there's the tunnel will establish on the one path, and as long as that tunnel's up, it'll take it. So some of the benefits of running an offline calculation model for your RSVP values is that you don't actually need your head-ends to do the calculation, and you get generally stable pathing. If the tunnels have to constantly be recalculated by the head ends, it could find a better path and shift around. The drawbacks are that you can have inefficient usage of your bandwidth during non-hot times on your network. It actually takes quite a bit of programming to be able to do your calculations, and it's very highly dependent on your stats collection, meaning that if you have some problem with the storage or whatever, or the retrieval of the data, it can wildly skew your RSVP reservations. So this is just sort of what I was mentioning earlier, where you have during most of the time, you'd probably want to calculate for maybe not your peak, but maybe a P95 value. So a lot of times you're going to have wasted bandwidth. And then during the peak, you'll have unaccounted for bandwidth. So benefits and drawbacks of doing online. It's a better reflection of your actual traffic. If you have a sudden surge in traffic on your network, doing an offline calculation won't pick it up. So if you allow the tunnels or the routers to run an auto bandwidth, it will eventually pick it up, but the traffic will trail and lead the actual reservation. So depending on how steep a curve it is or how much traffic is being unaccounted for, it may not really help you in time. And you have to use the vendor's heuristics instead of your own as far as stating, why I want to run at a certain bandwidth or whatever. Here's an example of what I mean of trailing and leading the actual traffic. You have a threshold, which is the bar there, of, this is my static reservation, or not static reservation, but this is my reservation. The actual traffic is growing along the bell curve there. So as traffic's ramping up, a lot of times the actual traffic will be higher than what you're reserved because it's being run on the traffic from a previous time. And then on the flip side, you'll actually have more reserve than you actually need. So there's a couple of causes of tunnel failures. Most common is usually circuit or IGP failure. Sometimes if there's absolutely no reservable bandwidth, the tunnel can actually not establish, and then it'll just ram through on IP. And the other two, not really too common. So just wanted to mention this real quick, soft preemption. It allows the tunnel to continue forwarding traffic while another tunnel establishes. It's something that actually someone at my current job and someone at my previous job worked on together with a couple of the hardware vendors. Juniper has already implemented it, and Cisco says that they're planning on it. So that will actually greatly help the black holing issue. So some considerations. I'm not saying I have answers to any of these, but so one of the things I mentioned earlier is it better to have traffic running along a suboptimal path all the time, or would it be better to have traffic run along the suboptimal path if there's not full resource available to it, and then as the traffic levels die down, allow the tunnel to go over the specific path, the more optimal path. I don't know. What's a better way to handle the larger flows in traffic? Should we have smaller tunnels? Creates more state on the routers, possibly running into ECMP, equal cost multipath problems. Is it better to have smaller number but larger tunnels? Are they better off on the core or the edge? That's a whole design philosophy as far as, do you want to have a dumb core or a dumb edge? How do you want to calculate your reservations? And another interesting issue is how to account for sudden surges in traffic, such as if traffic would normally hairpin a specific router, suddenly there's a failure, it has to actually hit your backbone, and your reservations are all out of whack. So the bottom line is, I've found that using tunnels allow you for more control over your traffic in your network. Allows you to defer some OpEx and some CapEx costs, but on the flip side, there's more moving parts. You do need to spend the money on your hardware. It takes more engineering resources, and the bottom line is it still takes money to make money. So, any questions?
Wow, looks like the crowd is silent there. Deafening applause.
All right.